Okay, so good evening everyone. Welcome to the Chemistry Frontiers. Today I am going to discuss about a very important topic, which is concept of reduction potential. But before going to the concept, we should know that why we are so much eager to know the reduction potential concept. So in our previous class I have already talked about a very important topic, that is called oxidation and reduction, and I know that you all are already familiar with oxidation reduction in your redox or electrochemistry classes. But okay, in a similar fashion also we should know the thermodynamics of each and every oxidation reactions which will happen in organic chemistry, how we can correlate our electrochemistry concept here also, that we will look into this, we will look into that matter in this class. So now let's basically start from a very beginning. Okay, so what is basically, if I ask you what is basically oxidant, what is basically, sorry, just a minute, what is oxidant? If I ask you what is oxidant, so very important, that means the species having higher tendency of accepting the electron. But my question is that if we are performing an organic reaction and we are using any particular oxidant to oxidize, let's say any alcohol, let's say we are taking one alcohol. Now we are interested to oxidize this particular alcohol to some species, let's say acetaldehyde. So now my question is, what should be the oxidant to drive the reaction in the forward direction, towards forward direction, to drive the reaction towards forward direction? What should be the oxidant? We can't choose randomly. So in order to choose a particular oxidant to drive this reaction towards the forward direction, we should have a profound knowledge about the reduction potential, and we should match with the substrate, okay, upon which we are interested to do oxidation reaction. So for that we should have a fundamental background of reduction potential. Let us try to introduce the concept of reduction potential. Why we should know this, we will talk about that thing, that matter also, step by step. Okay. I think that everyone basically now prior to introduce the thermodynamics, I would like to introduce the reduction potential. Okay, so reduction potential is nothing but basically we can basically we can explain it in a very simplified way, that the potential is a measure of a chemical species to gain electrons. So in a very very simplified way we can define it that it's a measure of chemical species tendency to gain electrons. That means from here we can say, we can basically draw a very important conclusion, that is higher is the reduction potential stronger oxidant. I think I am clear. I can make the concept of reduction potential very clear. Is it clear? If you can't understand up to this, please write in the comment box, then I will try to clear your doubt. Okay, let's try to understand that why higher is the reduction potential suggests us a stronger oxidant. Let us try to understand. So from very basic thermodynamic equation is delta G equal to delta G0 plus RT ln K equilibrium. I think everyone knows this particular equation. Okay, so for you know that where delta G is basically Gibbs free energy, this is nothing but the Gibbs free energy, and delta G0 is basically Gibbs free energy at standard state. That's why there is one superscript 0, so it indicates the standard state of a particular reaction. Now let us write a very common reaction. Okay, let's say alpha A plus beta B, that is basically Kb, comma C plus delta D. if I ask you what should be the K equilibrium, so in K equilibrium you can write very sorry ask you, so this should be the K equilibrium, and we can write it in this fashion, that C to the power gamma into D to the power delta by A to the power alpha into B to the power beta. I think up to this it is clear to all of you. This is very I will whatever I will write in the basically in this section, that is nothing but a very simple mathematics, and I think that we know all these things. Okay, so let's basically consider this as equation 1. Now if we just put the value of K equilibrium in the equation 1, so what will happen? So delta G equal to delta G0 plus RT ln K3, that means RT ln I am writing this equation again to understand you. Okay, so basically so that you can understand this, so in place of delta G you can write minus M A delta E. Now delta G0 you can write minus NF delta E0 plus RT ln K equilibrium. Now we can write delta E equal to delta E0 minus RT by NF ln K equilibrium. Now we can write delta E equal to delta E0 minus, everyone knows about the value of R, that is gas constant 8.314 joule Kelvin inverse mole inverse into temperature is 25 degrees centigrade, that will be 298 Kelvin. N is basically nothing but the number of electron transfer during the redox reaction. F is basically nothing but the Faraday constant, that is 96,500, and then you can write it basically to convert ln, because you know the base of ln is E, so if I want to convert ln to L log, so we have to multiply it with 2.303 log K equilibrium. So this equation I have written at room temperature. Now if we just think about I am doing very basic mathematics, very basic algebra. Then think about this delta E0 minus, if you just simplify this portion, this portion, it will give you 0.059 by n. Okay, that will be log K equilibrium. You know what will be the, you can put right here C to the power gamma B to the power delta A to the power alpha and B Okay, up to this I think it is clear to all of you. Now basically you can understand that what I am trying to teach you. So up to this is clear. So here basically you can understand that this N is nothing but the number of electron transfer during any redox reaction. Okay, so now we should know that factors that can affect the delta E. Okay. Okay, so let us try to understand a very important concept. That is, let us consider one very common organic reaction. Okay, so before going to that, I would like to introduce one very important. So we have written delta G0 equal to minus NFE0 cell. I think this up to this you know this. Okay, this is a very important reaction, sorry, very important equation, because if you look into it very carefully, so if delta G0 is positive, then non-spontaneous reaction, that means thermodynamically impossible. If delta, that indicates reaction under equilibrium. If delta G0 is negative, that is negative, this is spontaneous reaction. So when delta G0 will be negative, delta G0 will be less than 0 if and only if E0 cell is positive. So now we have to understand that from where we can get the E0 cell value. Okay, so let's say we are writing a very let's say very basic reaction, that is nothing but zinc, okay, solid plus copper 2 plus, okay, this is aqueous, that is basically providing zinc 2 plus, that is aqueous plus copper, that's solid. Now the concept of reduction potential, why that is important, I am just explaining you. Okay, in the next lecture I will discuss about in terms of organic reaction, how we can implement this reduction potential concept in organic reaction, that I will discuss in the next class. In this class, just let us try to build up the concept of reduction potential and its how we can discuss about reduction potential from thermodynamics that we will learn in this lecture. Okay, so I have written this reaction. Now whether this whatever I have written, is this correct? Okay, that means what is happening? What is happening from gene to gene 2 plus that is another redox reaction is happening. Copper, okay, 2 plus 2 copper. This is nothing but oxidation. This is reduction. Now let us try to, okay, one thing is that note down all the reduction potential is measured with respect to standard hydrogen electrode as reference electrode. Standard hydrogen electrode is basically, in short form we can write SH. So let's write. So reduction potential of copper 2 plus, aqueous, two electron that will be converted to copper solid, E0 copper 2 plus. This is called the reduction potential, 0.334 versus SH. Means copper 2 plus will be converted to copper if we apply this much potential with respect to standard hydrogen electrode. Okay, now zinc solid to zinc 2 plus extremely sorry, you can basically, if I write in reverse means in similar fashion, zinc 2 plus, this is aqueous plus 2 electron that is getting converted to zinc solid. Here E0 zinc 2 plus zinc is equal to minus 0.77 volt. Okay, so from my just before some time I have already talked that reduction potential I am writing again, higher means stronger oxidant. Now tell me, this is reaction 1, this is reaction 2. So among copper 2 plus and zinc 2 plus, which is stronger oxidant? So you can understand reduction potential of copper 2 plus, so copper is higher than E0, zinc 2 plus, zinc, right? Now let us try to understand that what is the basically physical significance of this statement, that higher is the reduction potential means it will be stronger oxidation. How we can say this? So to say this, I have already told that delta G0 should be less than 0, and for that E0 cell should be positive in value, right? Now if we subtract like this way, E0 copper 2 plus, copper minus E0 zinc 2 plus, zinc, right? That will be equal to 0.33 minus of 0.77, that is equal to 0.33 plus 0.77, that is equal to how much? 1.10 volt, which is basically greater than 0. That means E0 cell greater than 0. That means delta G0 less than 0. Am I clear? That means from as delta G0 is less than 0, that means the reaction is thermodynamically feasible. That means we have written this reaction, that we have already written zinc solid plus copper 2 plus aqueous, that will be converted to zinc 2 plus aqueous plus copper solid. Now you can ask me this question, that can I write? So this is basically okay, means this reaction is thermodynamically feasible. But let's say, based upon our curiosity, can we write? Okay, and another thing is very important that I have actually I have not told you. Of course, always you should write in this fashion. Okay, I am just writing. There are basically two compartments in a cell. There should be two compartments. Okay, means in cathode and another is anode. So cathode means where reduction will take place. Cathode means reaction oxidation reaction. When we write E0 cell, always we have to write E0 cathode minus E0 anode. Now let us try to verify whether I have already mentioned that this reaction is thermodynamically feasible, because I have basically proved that if we keep zinc solid, that means this species is getting oxidized, zinc is getting oxidized, that means it is anode, and copper is basically getting reduced, that means it is in cathode. Okay, let's say here for this reaction E0 cell, I have told you already that cathode minus anode. So cathode means where reduction is taking place. So from here to here, what is happening? That is reduction. So we have to write E0 cell is equal to E0 zinc 2 plus zinc minus this is reduction, sorry this is oxidation. That means we can write E0 copper 2 plus 2 copper. If we write this, then what will be the, we know what is the reduction potential of zinc 2 plus 2 zinc, minus 0.77 minus 0.33, that is minus 1.10, that is basically less than 0. Delta G is greater than 0, that means thermodynamically not feasible. So we can write, so this reaction is not thermodynamically feasible. So we have written this reaction wrong. Okay, I have proved why we should say that higher is the reduction potential, means it is a very strong oxidizing agent, stronger oxidant. Okay, I think up to this it is clear. So in the next class I will teach you about a very important thing, that how the reduction potential will change with pH, what is the concept of formal potential. Then I will introduce the concept of reduction potential in organic chemistry. So up to this, if you have any basic questions, any doubt, please feel free to write in the comment box. I will try to answer one by one. So thank you so much for showing this interest to see my video. Okay, I will try to transfer my knowledge to you. Whatever I know, how much I know, I will try to transfer that, so that you can understand the organic chemistry also from the thermodynamics point of view, and how we can choose a particular oxidant against a particular oxidation reaction. That I will discuss in next classes. Okay.